Okay, and then it's a great pleasure to announce Michael Kiessling from Rutgers University, so which is in fact like close to New York City for all of you who don't know where this is. And he's working in mathematical physics, relativistic physics, and he'll give a talk on the general relativistic quantum mechanical spectrum of hydrogenic ions.
Thank you, Felix, very much. I'm very happy to be given this opportunity and see you also online, unfortunately only after a long time, and the number of people who I have not met and some that I did. Okay, so this is a talk about joint work that I will, there we go. But before I get there, briefly the outline of the whole talk. This is giving an introduction. In this introduction, I will review a little bit just what everybody knows, presumably, about physics in the sector of the hydrogenic spectrum, quantum mechanical spectrum, and without gravity. And so then the rest is gravity. And at the end, there's a little bit of an epilogue. But as I said, it's a joint project. Here are my two collaborators. That's both are colleagues of mine. Shadi is full professor and works also in the mathematical physics group, but was originally trained in hyperbolic PDE and wave maps. This is Ebru Toprak. She is assistant professor in our department. Hill, assistant professor, very good and currently on the market. And so we have two papers out. This one just got published. So can you, by the way, see when I move my cursor here? It's okay, very good. So this is the paper that contains most of the material in this talk that deals with the gravitational problem. And some of the results of this paper will also be mentioned, but this is still under review in general relativity and gravitation. Okay, so here's the prologue. As I said, I want to give you first a zero gravity refresher. And the only difference to what you see in the textbook or introductory quantum mechanics course is, in this case, that for the Schrödinger Hamiltonian, I have added the rest energy of the electron. And in whatever I'm doing here, I'm really taking always the situation where the proton or the nucleus, let's say, the nucleus having Z elementary charges is fixed somewhere in origin of a coordinate system. In this case, you can speak of a test electron because it doesn't influence the proton or the nucleus, having charge, negative elementary charge, mass little m, and the mass of the nucleus plays no role at the moment. It will enter later in the general relativistic setting. Even though the nucleus then is still fixed, it's the ADM mass that will enter. And so you can think of the electron rest mass as a remnant of special relativity. And so you will see a lot of color in the formula, so that helps you keep track. So the green will always be associated with the electric part. This magenta is standing for C, and then it will be red later on for the gravity parts. Right? So, okay, so here's then just the Schrödinger Hamiltonian. Let's briefly review what's known, of course, for a long time, that this operator is essentially self-adjoint for all Z. And Z, by the way, of course, should be positive. It has an essential spectrum, which is a half line, which is above the rest energy of the electron. And that happens to be totally, absolutely continuous. So there's no singular continuous spectrum. The point spectrum.
So Z should be negative, right? So that you have a positive operator.
C should be negative.
Z, sorry,
No. The point is actually the operator is not always positive here. Actually, when this Z gets too big, it dips below zero. Okay, so when you remember that in the textbooks, normally this is not even there, the rest energy, and then all the bound states are negative.
Yes.
Yeah, and so when you make Z bigger and bigger, the bound state energy goes down, 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 like Z square. So eventually you become negative here. But that's the remnant of the fact that, of course, this is a non-relativistic operator. No? So it exists for all Z. It's essentially self-adjoint, but it's not always positive. But it's bounded below. That's the important point. Okay.
So what? No, sorry. It's bounded below because of this MC squared term, or
no. It's bounded below because of a Sobolev inequality.
Because of the Sobolev. Yeah, right. I'm sorry. Of course. Yes.
Okay. Okay, let's go on. So I was at the point spectrum, which coincides with a discrete spectrum. So there are no embedded eigenvalues in a continuum. That's what I already expressed here. So that's a little bit redundant. So you will see this kind of listing several times when I go on to different operators. So here I'm a little bit slow. Later I go a little bit quicker. So of course, the discrete spectrum is completely known. It's the Bohr spectrum. The only difference is that because I added the MC square here, you also see an MC square there. That's exactly this contribution. And if you multiply the MC square into it, the negative part, that's the bound states of the Bohr spectrum. And so here, of course, because of the Z here, you see that this becomes eventually negative. And one has bound states for all positive Z, and that is just a reminder that the combination E square over H bar C in my units is the Sommerfeld fine structure constant. And so the interesting thing is that for small Z, the Bohr spectrum is in fact very accurate, of course, and that's why it was recognized so early as a real success story. On the other hand, if you take the combination Z times alpha equals 1 here, okay, that is Z alpha, then of course you get for the ground state where n is 1, 1 minus 1/2 is 1/2. So that is already 1/2 the rest energy for the ground state energy. And so that's definitely not reasonable to use a non-relativistic approximation for that anymore. You need a relativistic one. And I wrote special relativity is needed if Z is approximately 137, but of course, this kicks in much earlier. So the 137 comes just from this estimate here. All right, so let's go to relativity and just review briefly what you find in an advanced course in quantum mechanics, namely when the Dirac equation is introduced. And again, we take a test electron. In fact, here in this case, it's not so easy, if possible at all, to go to a real two-particle problem. Definitely not in quantum mechanics, not sorted out. And so therefore, let's stick with this situation where the nucleus is just fixed at the origin. Okay, good. So now here we have our Dirac Hamiltonian. Alpha and beta are the Dirac matrices. Here, when you define beta equals gamma 0 and beta times alpha k, so this is the vector of 4×4 matrices, to be gamma k, then you have the Clifford algebra relation here. That is, of course, I think for the audience well known. Metric is just the Minkowski metric. Here's the red that indicates gravity, namely gravity is 0 here. That means you should think of this as indicating capital G, the Newton constant, being 0 here. And it's just flat space metric. And what is known is that this Hamiltonian is essentially self-adjoint on compactly supported C infinity bispinors away from the singularity. But if and only if Z times alpha is not bigger than 1/2 square root of 3. That's the result of Weidmann, from the Joachim Weidmann from the 1970s. But it has a unique analytical self-adjoint extension, which is essentially self-adjoint if and only if the Z times alpha is not bigger than 1. And that was shown by Heide-Nahnhofer also in the 70s. And so there are different ways to think about this analytical self-adjoint extension. So analyticity refers, you go to generalize Z to a complex number and allow non-Hermitian operators also, and then you go in the in the sense of a complex analytic extension, but if Z is then real, you can push it all the way to saturate this inequality. But physicists like to think about this a little bit differently, namely that the Dirac operator, of course, has what physicists call the kinetic energy part and the potential energy part. And if you demand that not only the Hamiltonian itself, the sum of the two gives you a finite result, but that the individual terms give you a finite result, then this restriction leads exactly to the analytical Selvitron extension. And what goes wrong if Z alpha is bigger than 1 is there's some a little bit of a hand-waving argument, is that the reason, first of all, why quantum mechanics is stabilizing in the physics lingo is that somehow there's a kind of angular momentum barrier, right? So, and the electrical attraction between electron and nucleus will overcome this angular momentum barrier when Z alpha becomes too big. So that's roughly the intuition behind this. And I will get back to this intuitive picture. So the first shock, of course, came when Dirac, was it Dirac? I think Gordon and Darwin solved the Dirac equation for this situation first. And they found that there are two continua, right? So this part is well known from what I showed you before in the non-relativistic setting, but now there's also a negative continuum. This was, of course, later shown that there's no singular continuous spectrum. The discrete spectrum was completely known too, interestingly. That's one of those amazing coincidences in quantum physics, that this is a Sommerfeld fine structure spectrum that was computed, well, not exactly by Sommerfeld, actually, but by one of Sommerfeld's associates. Sommerfeld made an approximate computation, so he did a power series approximation, and of the defining equations, and he sent it to one of his associates, or either a student or postdoc, and that person got back to him, and I think it was Lenz, but don't take me literally here, so I may misremember the name, and said, oh, Sommerfeld, I figured one can solve your equations completely, you know, so you don't need to approximate it. And so Sommerfeld included that. He gave credit to his associate in his paper, but still it became then known as, and for good reason, I think, as the Sommerfeld fine structure formula. And this is exactly giving you the discrete spectrum of the Dirac Hamiltonian, even though Sommerfeld didn't know about spin, didn't include it. And so how is that possible? No? So that these two very different ways of thinking even about what you are doing and what you are doing give you exactly the same answer. And there's a very beautiful paper by Stefan Keppeler from Tübingen that explains what kind of coincidences happen that you get with the Bohr-Sommerfeld quantization rules, in this case, exactly the same answer. There are some miraculous cancellations going on. What was shown in the 80s, first by Behnke, and then Geshtesi, Simon, and Thaler later, it's in Thaler's book, that's what I mean, that if you add to this operator up here, an operator that stands for the interaction of what is called the anomalous magnetic moment of the electron with a gradient of the Coulomb field of the nucleus, then you get an, and I wrote the amplitude is mu A for the A for anomalous magnetic moment, then you get an essentially Selvitron operator for all Z. So this is, of course, in some sense, giving you some relief, because it's known that the electron does feature an anomalous magnetic moment. And here, this I took from a Thaler publication, not from his book. In a book, there is a very similar picture. And this is from a review in a chemistry book. I'm sorry, in a chemistry, is it a book or is it a special proceedings? Maybe it's a book. collection of reviews. And so this is the spectrum here. In units, he has, of course, different notation. This minus gamma is z times alpha in my notation. And z times alpha being 1, here's the 1. This is exactly the endpoint of the essential self-adjointness of the Dirac-Hamiltonian, of the analytical extension of the Dirac-Hamiltonian without magnetic moment. So this is the ground state, energy hitting 0 here with a vertical slope. And but if you add an anomalous magnetic moment, you compute the eigenvalues, you see there are deviations, and they continue, but they eventually hit the lower continuum. And that's actually interesting. In the physics literature and also in Talos' book, you find a statement that they dive into the continuum, but that's not true. It's a result of Joachim Weidmann, that the continuum is absolutely continuous. There are no embedded eigenvalues. So they terminate here. And something that to my knowledge is not yet proven, but what is visible here, and that's an interesting phenomenon, that whenever the energy is 0, there are 2 eigenvalues that cross. So there's an accidental degeneracy going on, and to the best of my knowledge, nobody has shown why that is so. So this is just a side remark. But we are not yet at gravity, so let's go on. Let's raise the question. So how does intrinsic gravity influence the spectra? And I say intrinsic because I do not mean you bring an atom close to a neutron star or something like that. What I mean is you take the gravitational interaction between the nucleus and the electron into account. That's what I mean by intrinsic gravity, okay? Good, so here's a whole slew of statements. And so I begin with a really wide-held opinion, and it's not an unreasonable one. And that statement says that the intrinsic gravity, that means the attraction between electron and nucleus, is too weak to be of significance in atoms. And there is clearly an element of truth in that, but we will see that this is a very tricky proposal here. So here, why should that be true? Well, intrinsic Newtonian gravity is weak inside atoms and ions. So by weak, I mean relatively weak. So relatively compared to the electric interaction. It's also known that Einstein gravity reduces to Newtonian gravity for weak static fields. Therefore, it's true for Einstein gravity, QED. So that's a little bit of a soft argument, but that's the argument given. And well, here's the point. If you find this compelling, then prepare for some surprises. And so at least, even if it's quantitatively a very, very weak interaction relative to electricity, but we would at least expect the following effect, which is dramatic, at least where it happens. Namely, I had earlier mentioned that the reason for failure of essential self-adjointness is, well, at z alpha equals 1, was that the electric attraction overcomes the angular momentum barrier. And now gravity is attractive, right? So it should worsen that effect. So you should actually find that you cannot push z as far as you was able to push it before, right? So that's at least what one should expect. Okay, so therefore, let's look at what you find in the book of Greiner et al. On quantum electrodynamics in strong fields. Namely, because gravity is weak, you say, well, I can just work with Newtonian gravity. So it's some not really truly relativistic treatment now. And you take the Dirac equation, and besides Coulomb, you also add the Newtonian gravitational interaction. And oops, here we go. So, and that's what I just said. So now, first, actually, again, very quickly, the Schrödinger Hamiltonian with one difference. Since gravity is attractive, before I had a minus sign here to get bound states, but since gravity already provides a minus sign, I could also put a plus sign here and discuss a family of 2 different Schrödinger operators. And you can think of this as an electron having either a negative or positive charge, namely electron or anti-electron here. Okay, again, self-adjointness as before. What is interesting is the point spectrum or discrete spectrum. And so there's a difference here. This comes with a plus and this with a plus minus. Unless I try to pull it out and bring it here, that's not a difference, but these are the two things. So we have, as before, electron bound states for all capital M and all capital Z, but so-called positron bound states only if the mass is big enough, right? Or put differently, of course, Z should be an integer, but if I allow Z to be a positive real number, that means there will be positron bound states for very small z, right? But electron bound states for all z. And why is that so? Well, okay, let's take z again to be an integer. Then you can make M very massive, and I call that hyper-heavy. Hyper-heavy nuclei can bind a positron by gravitational attraction and overwhelm the electrical repulsion. And the reason I do this is because it fits into what you will see in the Dirac operator in the next moment. So, of course, with the physical parameters, this is a tiny, tiny ratio here. So hyper-heavy is really very hyper-heavy. Okay, so now we get to the Dirac operator. So here is how you add simply the Newtonian gravity into the story, but notice that it couples differently from Coulomb. Yeah? So Coulomb is with a 4x4 identity matrix. Gravity couples with a beta matrix, which is a block matrix having the identity and negative identity in the diagonal blocks, if I use the usual representation that Dirac used. And this is as before, but here's the first surprise. Okay, so that's the first time we encounter that our intuition was wrong. And that's actually one of the themes of this talk. I will intend to surprise you at every corner and share with you the surprises that we experienced when we were working on this. Switching on Newtonian gravity, even though it adds to the attraction between electron and the nucleus, actually helps, right? It doesn't make the essential self-adjointness worse. If G is 0, this is the criterion of Weidmann. It's just squared here. I didn't want to put square roots. No? So this less than 3/4 is Weidmann's result. But if I switch on gravity and enhance the attraction, I can push Z to be bigger, right? And I still have essential self-adjointment. Of course, this is ridiculously tiny in terms of quantitative numbers, but still qualitatively it goes in the opposite direction of what one was naively expecting. So, and we were indeed quite baffled to find this. Same with the analytical extension, you can push this beyond 1, but not much, no? By the same tiny amount. So that's the conclusion. Huh? So it's only a tiny bit, but it regularizes the operator. Wow. Essential spectrum as before. And you can compute the discrete spectrum. So the minus sign up here is the electron spectrum, if you want, and the plus sign refers to the positron spectrum. But you should match the signs here, that the upper sign here corresponds to the upper sign there. So it's minus here corresponds to plus there, and a plus there. And there's an abbreviation here that I put below. And by the way, when you look at this expression here, that's a giveaway. That's a giveaway for what you see up here. Okay, so we continue. You summarize that from that big formula that I just showed, that electron bound states exist whenever this inequality is true. That was just referring to this bracketed term under the square root that I was showing. Positron bound states only if the mass is big enough compared to this. And that's the same criterion as for the Schrödinger operator, interestingly, this one here. And here's a side remark. The positron spectrum is always less than 0 here. Not so for the electron spectrum. I mean, I'm talking about the discrete states. Huh? They can become negative. However, they are ordered. Oh, there's a typo here. This is a minus is correct. This should be a plus. So the electron spectrum part never crosses with the positron spectrum part. So this sits always below. And sorry about that. There should be a plus in. Again, laboratory ions, you have this very tiny number for this ratio up here. So you get only tiniest corrections to the G equals 0 Sommerfeld spectrum. And so that indicates that indeed the expectation that physicists have that it's irrelevant is quantitatively panning out, except for the surprise result that you get a regularization instead of a destabilization near the critical value for the essential Salvajoiners. And okay, so what about if this is violated? Not violated, I mean, if you do get positron bound states, that means if you M is violating the laboratory bounds, that's what I mean. So you get to the hyperheavy nuclei. Well, yes, you get a positron spectrum that is not trivial and is gravitationally coarse, but this inequality, together with this empirical observed rule that the mass of an ion, of a nucleus, is, well, if Z is 1, then I can actually put an equality sign here. But otherwise, it's bigger than Z times M. That's an empirical rule. If you take these two together, then you deduce that also this inequality has to be true. And that means we actually are in the black hole sector of a Reisner-Nordström black hole. So that would not correspond to the traditional concept of an ion, right? So of a nucleus that can be surrounded by an electron. And this thing here would actually correspond to a situation that doesn't exist in general relativity. On the other hand, one could, of course, say, what do we know whether this empirical laboratory rule will be true? No, I'm sorry, this is true. So I take back what I said a minute ago. I said you cannot reach this with laboratory, sure, because in a lab you cannot make big M, but also this laboratory rule is needed mathematically to say this cannot be reached. You cannot make this together with that. But this now we can say to hell with it. What do we know whether this is true for large M? And indeed, if you think neutron stars definitely are expected to have an M much, much, much bigger than Z times the proton mass. And the Z is the charge of the neutron star. And of course, neutron stars are not points, but this is just making a point that in principle, one can think that nature may have produced some gigantic collapsed objects with a big M and a small z, and then that may become relevant to look at this gravitationally created positron spectrum. So just a brief list of remarks. So the discrete spectrum you find in the book by Greiner, Müller, Rafalski on quantum electrodynamics in strong fields. Interesting, again, even with Newtonian gravity, you get the spectrum also from the Bohr-Sommerfeld rules. And if you ignore fine structure, it looks a little simpler. Then this looks like that. That means you work only with the circular orbits right now. So you are minimizing this function with respect to R. And then you get exactly the spectrum I showed you, except for the fine structure. So you get the main lines. And you get the same result here that before, that an infimum here exists if and only if this inequality holds, right? That corresponded to the endpoint of essential Salvajoiners. So I adapted the result from Nahnhofer and also from Weidmann to come to these conclusions that I had stated. And so the question is the electron's anomalous magnetic moment restoring essential Salvajoiners? Well, actually that hasn't been checked out, and we want to look into this. We did check out these questions in general relativity, but we didn't do it for the Newtonian gravity case in special relativity. Good, finally, general relativity now. So after all these preparations, we are prepared to go on and do real relativity. So now we look at the Reisner-Weil-Nordström spacetime of a nucleus. So here's where the M already comes into the spacetime, not, of course, as a dynamical thing. Test electron again. We make this restriction here so that I don't go into the black hole sector. We'll go to black hole later. For the Reisner-Weil-Nordström spacetime, we have this metric function f, here's f square, and if you set z equals 0 or equals 0, you get Schwarzschild, right? And if you set g equals 0, then you get Minkowski. Electromagnetic four potential is just that of the nucleus. And here's a little bit of interesting history, namely as soon as Sommerfeld in 1916 published his Bohr-Sommerfeld results for the spectrum of hydrogenic atoms or hydrogen, he was criticized by Vereide, a Norwegian physicist, for not having done the calculation general-relativistically. Actually, Sommerfeld had consulted with Einstein. He said, shall I do it general-relativistic? And Einstein said, don't bother. The results will be so close that it's essentially the same, no? So don't bother. And as soon as then Sommerfeld did publish without general relativity, he was criticized for not using general relativity. And but Vereide didn't get that far. But then Vallata is a Mexican physicist who did a PhD at MIT in 1924, applied these Bohr-Sommerfeld rules, and he did show, and that was his goal, to confirm what everybody expected, that general relativity makes only the tiniest corrections. And the interesting thing is that mission accomplished, that he actually estimated how much the discrepancy could be. Then he didn't actually bother to compute any effects. Is there a splitting of lines or anything like that? So he just stopped at the estimate. And the point is, had he not merely tried to confirm what everybody knew, he could have made a startling discovery. So I'm preparing you for the next surprise. And here is the surprise. And I put it in a box so that it stands out right away. The surprise is that general relativity in the Bohr-Sommerfeld quantization completely stabilizes the hydrogenic problem. There is no more catastrophe. Yeah? So when in the Newtonian gravity case, it was already a surprise that it was doing something in the opposite direction of what we expected. We thought that it should destabilize, right? It was stabilizing by a tiny amount. General relativity stabilizes completely. It stabilizes completely. So here's the function that needs to be minimized if you only work with circular orbits for simplicity, to make it not too messy. So you look for the minimum of this kind of energy function that depends only on a radius. I, in this case, put minus plus here, so I am allowing also a positron here in the field of the nucleus being attracted by gravity. And so both cases are here. You see, this is the special relativistic factor from what already shows up in Sommerfeld's calculation. And this is a factor coming from general relativity. That's the only square root where you see a G. And so there is a minimum of the U with a minus. That means for the electron, for all Z, and as long as these square roots, of course, are under the square root, you have a positive number, as long as the square roots are real. So that's why I have this restriction that takes care of that. There is also a minimum for the positron, but only if this inequality is true. And this here is needed now to keep the square roots real. No? So this was not there before. This here is the inequality we have seen before already in the Schrödinger equation, that the gravitational attraction overcomes the electrical repulsion between a nucleus and a positron. But to avoid what we later know is the black hole, is also needed already in this theory. So, and here's basically the conclusion, right? While Newton's G regularizes just a tiny bit, Einstein's G regularizes completely. And this suggests that the Reisner-Weil-Nordström spacetime also regularizes the hydrogenic Dirac problem. right? So maybe we don't need the anomalous magnetic moment, right? Okay, so let's go and look at the Dirac equation in the Reissner-Wall-Nordström spacetime. So we have the same metric, and here's the Dirac equation now. The interesting thing is, of course, that whereas gravity, it enters through the Clifford algebra for the gamma matrices. So I'm just using gamma here, that this is now not the special relativistic gammas. I think Felix likes to put capital gammas here. And all right, here's the metric for potential as before. Let's rewrite the Dirac equation up here by using these coordinates. We rewrite it into the Schrödinger format, so you separate out the time dependence. It's a static spacetime anyhow, because we are in a naked singularity sector. And here comes surprise, surprise, surprise. Namely, so this was done for the first time, as far as I know, by Cohen and Powers, Jeffrey Cohen, and I forgot the first name, Powers, and in 1982, and then later picked up by Belgiorno and his associates, Martellini and Baldicchi, in 2000. Actually, there's also a paper earlier in the late 1990s, I mean. So, and it turns out that the Dirac Hamiltonian is not essentially self-adjoint for no positive Z, okay? And so that means the original intuition seems actually to have been correct. Gravity makes things worse, but you cannot use Newton gravity, and you cannot use the Bohr-Sommerfeld quantization rule, right? So, but if you go to general relativity, things are worse. However, there are self-adjoint extensions, infinitely many. And so the question is which one to pick, right? So that's a real problem. Now, in fact, we will see that it's maybe not quite a big problem because there's still the anomalous magnetic moment to be investigated, right? Good. So anyway, punchline is that the Reissner-Wall-Nordström spacetime here has a devastating effect on the Dirac hydrogen problem.
Michael, maybe just a short question. I mean, like, so I mean, you just said that it's surprising that the Hamiltonian is not essentially self-adjoint.
Given the result of the previous study that you take the Bohr-Sommerfeld quantization, right, and put that into the Reissner-Nordström spacetime, like Vallata had done, and then you find that there's no more collapse. No? Previously, when you take Newtonian gravity, only there is a collapse, which has the same critical Z value as you get from the Dirac equation with Newtonian gravity. And so that there is this fantastic agreement between the Sommerfeld spectra or Bohr-Sommerfeld spectra you get and the Dirac equation spectra. So one could expect that therefore everything you learn from Bohr-Sommerfeld should be true for Dirac in this context, right? And it turns out as soon as you go to general relativity, the answer is no, they are completely different.
And on the other hand, can this fact that it's not essentially self-adjoint be understood directly from the naked singularity?
Yes, exactly. The point is that what happens is that the Bohr-Sommerfeld theory works, of course, with classical orbits, right? And then you basically, it's a selection principle for orbits, but the orbits, in particular, when you take circular orbits, they never get close to the singularity. Okay. While when you work with bispin or wave functions, of course, they see the singularity in a naked singularity sector, no? And that's exactly what's going on.
I see. Okay, thanks a lot.
Okay, so back to the question, what happens when you add this anomalous magnetic moment operator, no? H sub anom here, and it was investigated by Belgiorno, Martellini, Baldicchi, and they find you can restore essential self-adjointness, but different from the Minkowski space setting, now the empirical magnetic moment has to pass a threshold. In the special relativistic setting, you just add any anomalous magnetic moment operator with the right sign, and but magnitude, amplitude is epsilon, let's say, no matter how small, you get the essential self-adjointness. Here you have to pass a critical value. That's interesting. But when you then look at the value of the empirical electron, the empirical anomalous magnetic moment, it turns out to be roughly 10 to the 18 times bigger than the mathematically computed threshold that you need to pass in order to get essential salvage jointness. So this is, we are on the safe side as far as physics is concerned. No? As long as you take the anomalous magnetic moment into account. No? In that case, it's known that you get the usual continuum, the positive and negative continuum, no singular continuous spectrum. They also showed that they means Giorno, Martellini, and Baldicchi showed that you have infinitely many bound states. And we are actually currently trying to get a hand on a discrete spectrum. It's an interesting numerical calculation. It doesn't look like there's any way with the traditional techniques to actually compute this analytically in closed form or anything like that. It looks like you may actually need the theory of trans series to get a hand on this, but I'm getting a little bit out of my comfort zone. So these are some indications, and I don't know much about trans series here. Okay. So I said general-relativistic hydrogen 2. Why? So far was the naked singularity sector. Let's go to the black hole sector. And Cohen and Powers studied also the Dirac Hamiltonian outside of the event horizon of a black hole. And they showed that the Hamiltonian is essentially self-adjoint when you take compactly supported C-infinity bispinors that are supported outside of the event horizon, okay? And, but the interesting thing is that the essential spectrum is the whole real line, so there's no gap, there's no point spectrum, therefore no point states, but it's not really surprising. If they use, of course, a coordinate system, which you can call the Schwarzschild coordinates, so that how an observer from infinity sees the space-time outside of the horizon. And so then in these coordinates, can there be a bound state? Now, presumably what you will see is either the, because bound state means you already assume that you don't escape to infinity, but what will happen is you will see that the bispinor will concentrate closer and closer to the horizon and not settle down. No? And the electron itself will be sucked through. And so that's not really a surprising result. And that raises the issue, since the Reisner-Wall-Nordström spacetime does have a static core region. So there are three regions. There's this outer region outside of the horizon, and then comes between event horizon and the inner Cauchy horizon, it's a dynamical region that, and then comes inside the Cauchy horizon another static region. And that is like a spacetime in its own right and with a naked singularity, but it's not asymptotically flat. So the question is, can that thing produce a discrete spectrum? That's the question we ask. And here's the first result of my collaboration with Ebru and Shadi. And that is the paper that is still under review at General Relativity and Gravitation. So we did study the Dirac operator in the interior of the Cauchy horizon. That means we took a single component there. So, and here's what we found. It's not essentially self-adjoint, which is not too surprising. It's the same naked singularity that also we had before in the naked singularity sector. Has infinitely many self-adjoint extensions. Okay, of course, we don't know which one to pick here. And we also know that adding a sufficiently large anomalous magnetic moment will produce essential self-adjointness, and it's the same critical value as before. And by the way, that is again this 10 to 18 that I mentioned earlier as a factor. So that I want to point out, when you look at the expansion that people write for what is the anomalous magnetic moment, they always write it as a power series in alpha, and then it comes correction that also have powers of log alpha in there, but multiplied by the Bohr magneton. Yeah, but alpha is E squared over H bar C. Now the Bohr magneton is proportional to H bar. So the first correction term actually cancels the H bar, and that is this. Yeah, so there's no H bar in this term, and that already gives you something like a 3 or 4 digit precision for the anomalous magnetic moment, and that's a purely classical expression, which is some indication, I think, that it's either pure coincidence and should not be taken seriously, of course, but it may be an indication that there is some tiny structure associated with the electron that is responsible for such a magnetic moment. No? While the Bohr magneton is produced by the quantum mechanics of the spinor. It's not associated with the particle itself, but with the law of motion, if you want. But here is the shock again. We expected to find bound states, and there are none, right? So again, the continuum is the whole real line. There is no bound states. So is that still surprising? We were surprised. I was not surprised not to see bound states outside of the event horizon, but I'm surprised that we find no bound states inside the Cauchy horizon, because the electron now cannot be sucked in anymore, right? It is already in. And so it's the existence of the Cauchy horizon now which destroys, which removes the gap, and the eigenvalues, if one takes this as a rule of thumb, they can only be in the gap. Then yeah, there's no gap, so there's no eigenvalues.
And Michael, again, it's a stupid question. So
yeah.
R minus, so at this Cauchy horizon, so I mean, there are no boundary conditions to impose because...
No, because we use the same type of... No, it's infinitely far away, exactly. Mm-hmm. Yeah. It's like the same kind of coordinate transformation that also Cohen and Powers used for outside of the Cauchy horizon. You push the, I'm sorry, outside the event horizon, you push the event horizon to 0, no? Exactly. And we push the Cauchy horizon to infinity.
So similar to these Regge-Wheeler coordinates, is it something similar which you are using? Like the Regge-Wheeler coordinate?
Yes, exactly. This tortoise coordinate type thing. Yeah, exactly. Mm-hmm. So it's, I mean, the details look a little different because the integral looks a little different, no? But otherwise it's the same type of idea. Okay, good. So, all right, next part. So not all is well though. No? So even though adding an anomalous magnetic moment gives you central self-joiners, and the problem is indeed here that we have an infinite electrostatic self-energy of the nucleus. So if you go a little bit, so these are just standard formulas here, but here this, when you look at that, so we have an ADM mass of the Reisner-Wall-Nordström spacetime, which is finite, and but we have an infinite electrostatic field energy in it. So, and that means this here is the energy outside of a sphere with area 4 pi r square. And so it gets subtracted, and eventually this will be 0 and become negative, and in fact become negative infinite, this whole expression. And this is basically the mass atop of the 1 over r term in a Schwarzschild type setting. And so you have what is called a negative infinite quasi-local mass when you shrink this sphere to have 0 radius. And so clearly there's, basically you can think of that as an infinite bare mass. So the question is, does that create maybe a singularity which is too strong? And if you use models with better electrodynamics, which have long been proposed, can that help? No? So first, of course, you may also say, oh, I'm not really worried, because when you compare what is the size of the proton radius, for instance, compared to this size of where the turnaround happens, no? where this suddenly becomes negative, then it turns out that you are way inside the proton, and you say, ah, then the model is anyhow not to be trusted because the proton has a finite size. Similar to saying the Schwarzschild radius of the sun is way inside the sun, so don't worry about it. True, one could make that argument and say don't oversimplify the proton, but if you think that protons consist of point quarks, and point quarks have also then electric charges, then you are only kicking the can down the road, and you face the problem later on. Now the way out would be the more regular electromagnetic field equations. And so this I really now go through quickly. By the way, do I have an hour or 1 hour 20? How is that? I couldn't hear you. Are you muted?
Sorry, I was muted. So I mean, there's no rush. I mean, 1 hour and 20 minutes is perfectly fine.
Okay, so I don't want to keep you too long, but so this is just a little bit of background on nonlinear electromagnetism. So this goes back actually to Gustav Mie in 1912. So he was one of the first to raise the questions, how unique are Maxwell's equations, right? And can we not overcome the infinity problems? He was exactly concerned with his infinity problems of point charges. The electron was, of course, discovered already more than 12 years ago. And he proposed that by using nonlinear field equations, you will get integrable scenarios. He actually wanted to get the point charge out of the picture and was thinking of solitons. He didn't know to call them so, but in any case. And but he did discover that to get a relativistic theory, you need a Lagrangian. And he wrote down what are the invariants that you should build it from. That was picked up in 1933 by Born, and then 1934 by Born and Infeld. And they put the point charge back into the picture, but also chose a particular Lagrangian that led to these kind of horrible expressions that replace what we use in Maxwell's theory. Namely, in Maxwell's theory, the law of the vacuum is that the electric field equals the electric displacement field, and the magnetic field equals the magnetic induction field. And me was saying this is the culprit here. That causes the problems because it makes linear field equations. Now, how do you go from here to here is a story that Pierre Linitsky-Birula called one of the amusing serendipities in theoretical physics. So this you don't dream up overnight. Huh? So the point is that Born and Infeld had an argument that led them to this, and they thought it was unique. It was later shown it has many other solutions. So this is not unique from their perspective. But in the 1970s, it was shown that for completely different reasons, this is a very distinguished vacuum law that was shown by Plebanski and independently by Guy Bolat. And so there are 5 postulates you need to make to end up, postulates regarding the Lagrangian. The Lagrangian has to be Lorentz and gauge covariant. That's 2 postulates. It should reduce in the weak field limit to the Lagrangian that gives you the traditional vacuum law. That's the 3rd one. The 4th one is that you don't want to have infinite self-energy of point charges. Obviously, that's the whole goal, right? So these 4 are completely compelling. And number 5 is that you do not have birefringence. So the Maxwell equations, the usual ones with this vacuum law, don't show birefringence in vacuum. And if you postulate that that should be true for the nonlinear theory, you uniquely end up here. So this is one of the reasons why I think it's worth really working on Born-Infeld field theory, but it's of course a horrible nonlinearity that makes life miserable, but also interesting. Good. Okay, 1935, just 1 year after Born-Infeld proposed this, Barnesch-Hoffmann said, let's look at what the analog of the Reissner-Weil-Nordström spacetime is in this theory. And he found, or we now take the nucleus parameter as before, right? And so there's either a black hole or naked singularity as before. But the interesting thing is now, previously in the Reissner-Weil-Nordström spacetime, it was only a competition between these 2 parameters here, m and z, basically, given E. Now there's a Born parameter B also in the story, right? When you look at this B is the only new parameter here. It's some reference field strength if you want. And so the borderline case, and you see here, yeah, there's m here and z, and it is m squared and z cubed. So that's, now if you play with B, you can have either black hole or naked singularity sector. Now that capital B here is the Euler beta function. Okay, so here is then what we will see. This is now the same metric written in F, but F looks different. Well, that part is still the same as before, but here we had just the Reissner-Nordström expression. Now we have this integral which cannot be expressed in elementary closed form, but it can be easily discussed, and the behavior gives you this conclusion that you have a positive quasi-local mass for all radii if B is less than the B Hoffman, H stands for Hoffman. And when you let B go to infinity, you get the Reisner-Weyl-Nordström spacetime, E to 0 Schwarzschild, G to 0 Minkowski. And the interesting thing is that if you take B to be exactly the Hoffman value, then you find that the electrostatic field energy equals exactly the ADM energy. Okay, so that means all the ADM mass is due entirely to the electrostatic field in a sense. And it has the mild conical curvature singularity at the origin that was shown by Shadi in 2011. So now Shadi put a PhD student on it, that was Mullik Balasubramanian. Meantime, this is submitted for publication, available at the archive. I forgot to put the data in. So he studied now the Dirac Hamiltonian on this spacetime when you are exactly at the Hoffman value. That means you have basically zero bare mass. And he found that the Hamiltonian is essentially self-adjoint here, the usual continuum. You have an infinitely many bound states. And this is something that he also has been working on to actually try to get a hand on the evaluation. There's not only a gravitational correction, but there is actually a much more dominant correction from the Born parameter. And of course, that's interesting to figure out what that correction is. That gives you information about how big the Born parameter can be, because you should not violate empirical data, right? So that's an interesting project to work on. And he actually generalizes this to a whole class of electrostatic spacetimes, all with zero bare mass. And the point is that you have an essentially self-adjoint Hamiltonian already without an anomalous magnetic moment. Okay, so that confirms the suspicion that the infinite electromagnetic or electrostatic self-energy was the culprit. That means it is due to a too strong singularity. Well, let's see. At least, yes, it confirms that intuition, and but is that the whole story? Well, there is a problem. Not all is well. And the reason is that to work with Hoffman value fixes that value once and for all, right? So for a particular M and Z. But of course, different nuclei have different M and different Z. And so then you do not have the corresponding Hoffman value for B. You know? B is to be chosen once, it's a constant of nature, and that BH depends on M and Z. So you can choose B only for one M and one Z, but not for all of them all the time. So therefore, what to do next is you should also look at the other regime, but we don't want black hole to have to describe an hydrogen or hydrogenic ion. So what we should do is look for the naked singularity sector. Now, this should be done later also, but this is what Ebro, Shadi, and I have done. We studied the naked singularity sector here. And then we, in the Hoffman setting, we can have any finite negative bare mass now. So basically what we are doing is negative bare mass sector, you can call it that one. And now the interesting thing is we are between the really bad Reisner-Weyl-Nordström singularity and the very mild Hoffman singularity when the bare mass is zero. So now the question is, where will the verdict be, right? Will it be essential self-adjointness, nevertheless, and it's only Reisner-Weyl-Nordström where you lose essential self-adjointness, or is there a critical bare mass value where it switches? So these are the two questions, and surprise, surprise, what do you think? Never essentially self-adjoint. So as soon as you have a negative bare mass, you lose essential self-adjointness. So it was a temporary relief what Mullik has found, but it's not a generic result, right? So generic should be negative bare mass, and then of course we have also nobody should frown about negative bare mass in principle. After all, we use it in quantum field theory all the time, and but this was a surprise. We were expecting actually that we would be on the side of essential self-adjointness, but we were not. So again, one surprise after another. We have infinitely many self-adjoint extensions. The continuum is as before. There are infinitely many bound states in the gap. We can show that plus mc square is always an accumulation point. We can show that negative mc square is an accumulation point of the discrete spectrum, if and only if this well-known inequality is true. That's an inequality that we found with Schrödinger's equation for positrons being attracted by the gravitational interaction, overcoming the electrical repulsion. But again, this is a naked singularity sector, and as I said, it's presumably not what you can achieve with nuclei. That's if the empirically known inequalities hold all the way up for arbitrary m and z. So we didn't yet investigate the black hole sector, no? But we did ask what happens with a anomalous magnetic moment. And here was another surprise. So in the Hoffman spacetime with negative bare mass, if you add an anomalous magnetic moment, the Hamiltonian is still not essentially self-adjoint, and no matter how strong the anomalous magnetic moment is. So this was a surprise. So this time it cannot come to the rescue. So there are always infinitely many self-adjoint extensions with the usual spectrum as before. And we, as I said, haven't investigated black hole sector. But this time, the interesting thing is all the time before, the anomalous magnetic moment came to the rescue, right? When we lost essential self-adjointness. Now it doesn't for the Hoffman spacetime. So we basically, here's the general result. We looked not only at the Hoffman, we generalized the electromagnetic spacetime. And whenever there's a strictly negative bare mass, you never have essential self-adjointness. You may or may not have essential self-adjointness with an anomalous magnetic moment. It depends on the vacuum law. Namely, the electric field must blow up strongly enough at the singularity, and it doesn't blow up at all in the Hoffman spacetime. So that's basically saying why you are out of luck there. And but here's just the same. That's okay. Some comments. So our spacetimes cover basically, it's a very large class of spacetimes, of naked singularity spacetimes that include Reisner-Weyl-Nordström and all the way up to the mildest singularity, zero bare mass Hoffman. We use separation of variables, of course, to conclude to our results. The partial wave decomposition that reduces the whole story to looking at operators on two-dimensional bispinor subspaces. So that reduces the discussion to a system of two linear ODEs, and we definitely make heavy use of the techniques of Weidmann and of work by Hinton, Mingarelli, Reed, and Shaw. And here are now my concluding remarks, and then I'm finished. And so basically the conclusion is that far from being merely a quantitatively tiny deformation of a special relativistic Dirac equation, right? The general relativistic Dirac equation, which I think was written down first by Schrödinger in 1932 and then pushed quite a bit by Brill and Cohen, 1966, is a completely different story. And we found that to develop intuition of what is going to happen is difficult, and we were, as I said, wrong at every corner with our intuition. And so, of course, with hindsight, you start building up a new intuition, but then the question is, how long will that be true until you are proven wrong again? And so there are many tough conceptual questions that still need to be sorted out. Now, I mean, we are only scratching really at the surface here. We really would like to get to a well-defined general relativistic quantum mechanics. No, we are not talking quantum field theory. We don't want to quantize gravity. And, but we want to basically generalize what we know we have for non-relativistic quantum mechanics, Schrödinger or Pauli equations with many particles, to find analogs relativistically, including general relativity. No? And clearly, if the effects, however, are quantitatively tiny, so this is really a job for mathematical physicists. I think that's the main thing, because you cannot rely on empirical input here from the lab. No, that's completely clear. Okay, thank you very much. That was it.
Okay, so thank you very much, Michael, for this nice talk. So thanks a lot. And then let me open the discussion. So any questions, comments? So just speak up, I guess that's easiest.
I mean, I just have sort of a question / comment. At some point, I've seen claims, like I haven't read the paper, but I just saw the claim that apparently some people say that like the muon magnetic moment, that the discrepancy can be addressed by including GR effects. Are you aware of that or something in that direction?
If you can send me the link or information of where you read that, I've not heard of that.
Yeah.
I mean,
okay.
I know that there is a puzzle between certain empirical measurements and QED, or what means QED, standard model calculations concerning the anomalous magnetic moment of the muon. That I know. And so, but I've never heard that general relativity is supposed to play any role. And so if you could send me that link, yes, that would be nice.
I will look up the source that I had. Yeah.
In fact, I would also be interested, Claudio. So just please send it to me too.
Yeah, I mean, I'll just search the article that I found. Like I think the paper should be linked there, but I just saw some sort of like popular science sort of level article about it. So,
and of course, people occasionally invoke quantum gravity arguments. So has that maybe something to do with that, or do they really mean classical GR?
I didn't really understand the point. I think it was about somehow classical GR or something, but I really didn't fully understand. But I had it. So the main thing I had this on my radar was because it was somewhere on the tick list of interesting with respect to things to look at in the causal Fermi system context, to see whether one could make sense of that. Mm-hmm. But I never got beyond just being aware of the claim. That's okay. So I can't really say anything.
And now you made me aware of that claim, and I'm not beyond that. Thank you anyway. Yeah.
Are there other questions?
Maybe I could ask a question.
Oh, sure. That's
yeah. So I don't know whether I quite understood the procedure. You consider the Dirac Hamiltonian in the a naked singularity regime of Reissner-Nordström. So this would mean actually that you consider like Dirac sections supported in the in this region where, you know, with the singularity around. So I would be afraid that I run into ill-defined questions. Then I mean, if I leave the global hyperbolic sector, I mean, what maybe this points into the direction of Felix's question before. So you need some additional conditions then, or how do you manage to get well-posed problems?
Exactly. No, that's exactly how we don't. That's the point. If you do not add this anomalous magnetic moment operator, right, then indeed the Hamiltonian is not essentially self-adjoint. The space-time, of course, is now static. That's good. And so you can think of this as being given by a single chart away from the singularity. You start with bispinor wave functions that are compactly supported and C infinity, but away from the singularity as usual. And then you find, what means that means that's Cohen and Powers found that in 1982, that, and not V, that's what I mean, but that the Hamiltonian is not essentially self-adjoint. That means you need a boundary condition. So how do you do that? That's what I had pointed out in my talk, that how do you choose this, right? So, and fortunately, in this setting, you still have the anomalous magnetic moment coming to the rescue, because the anomalous magnetic moment of the electron at least is so huge that if you add that operator to the Dirac Hamiltonian, then you do get essential self-adjoiners, and you don't need to worry about any boundary condition at the singularity. And then
so you consider this the Dirac equation on this non-global hyperbolic spacetime then, and still get some. I mean,
the Dirac Hamiltonian, at least with anomalous magnetic moment, happens to be well defined. Means essentially self-adjoint, and so you do get a unitary dynamics on this.
Okay, this surprises me completely, but okay, I have to look it up. Yeah.
So this is, but that, as I said, you find in the paper by with anomalous magnetic moment about Reisner-Nordström. That's Belgiano, Martellini, and Baldicchi, and so I can. I think I sent the paper to Felix anyhow, no? So you should. But you can also, that is published in Journal of Math Physics, but they are both on the archive. So you just look for Kiessling, Toprak, and Tavildazadeh, and so you find these keywords there. And of course, this is recorded, and you can look up I have a couple of references in the beginning.
Thank you very much.
Okay, sure.
Okay, maybe another question, Michael. I mean, so I still don't fully understand where this anomalous magnetic operator comes from. I mean, this is supposed to take into account QED effects. Is this correct?
What effect? I didn't hear that.
Some like quantum electrodynamic effects.
Well, actually, Born was originally arguing in 1933. He said that was after the first couple of attempts to quote unquote quantize electromagnetic field theory, and there were all these infinities over the place. Now, so that came also as a shock, because quantum physics at that time was thought to get rid of infinities, right? So there was first this infinite energy being emitted by a black body radiator, right, according to classical theory, and that made no sense. And then comes Planck's quantum hypothesis, and you find, now we have a finite amount of energy coming out as it should, right? And then there's the stability question of matter, of the hydrogen atom. Why do we not get arbitrarily negative energies? Here comes Bohr's quantization rules, right? So of course everything, what I call the dawn of quantum physics, right? It's and so that, and then came Schrödinger's theory, and you could see, wow, you get even lower bounds on the energy for n-body systems, etc. And lots of success stories. And so the expectation was all these infinities in electrodynamics that are associated with the Lorentz electrodynamics, they will go away once we quantize. Well, the opposite was true. Suddenly you had many more infinities, and the old ones were not somehow ameliorated. No? And so Max Born, then wrote that it's pretty clear. He said that the quantization rules are not to be blamed. It must be the reason that we are quantizing the wrong classical equations here. And that's why he said, let's look at something else. And he, in 1914, 2 years after Gustav Mie had published his first batch of papers, that was a time when Born was still an assistant of Hilbert. Then he worked on Mie's theory. So he was very well aware of that theory. And he also knew that Mie had actually taken the point charge out and wanted to find a completely nonlinear field theory that has localized solutions that look like particles from a distance. And he said, no, we put the point charge back in, no? And expected that then things would become better. It was only when Heisenberg and Cockle and Euler, when they did these expansions of that time, what was running under the name quantum electrodynamics, and did this formal expansions and got corrections to the Lagrangian for the Maxwell or Maxwell-Lorentz fields. They look very similar to when you expand the Born-Infeld Lagrangian. The point is, however, that in the Born-Infeld Lagrangian you get this, you get E dot B squared, and you get E squared minus B squared squared. These two things show up, and but they have coefficients that are determined by the single parameter B. So now you can choose B to fit one of the two coefficients that you get from the Euler-Heisenberg-Huckel expansion, but then it doesn't fit the other. Or you can say, oh, okay, we do it 50-50 or something like that, but you will never get exactly the same thing. So which means that the Euler-Heisenberg-Huckel Lagrangian leads to birefringence.
I see.
Right? And so there is actually some effort. I think there's a team in maybe of physicists in Erfurt. I forgot, but there are people that try to make laboratory experiments to see whether at strong fields you do have birefringence or not. The problem is the following. See, the Born-Infeld electron dynamics is of course a purely classical theory. It says on a purely classical level, you don't have birefringence. Well, that's the same thing that the Maxwell theory says too. Now, once you quote unquote quantize, however one stands with a result that comes out, because we know it's not a well-defined theory, but it's a successful scheme somehow that comes out. And we do get at least a theory so far that predicts there is birefringence, even though you quantize a theory that doesn't have any. So if you quantize the Born-Infeld theory, which in the weak field limit does become Maxwell theory, you should also get similar results on birefringence plus corrections from the Born-Infeld parameter. So I think it will be extremely, extremely difficult to cast a verdict here from looking at such fine details. And but I think one has to look at this Born-Infeld thing. I don't think it will necessarily be the right classical limit, but it's a very compelling candidate to look at, right? So if and also when you think of the 5 arguments that the 5 postulates that I listed for why one should do that, you can think of that as a chain of arguments, and there's one link that's the weakest link in the chain, yeah, and that's the birefringence thing, right? Okay, so when you drop that, you should replace it by something else. What should that be? Well, you want a nonlinear field theory as regular as possible. You don't want that it keeps blowing up after a short time with epsilon initial data already. So for instance, a no shock condition seems plausible. And that has been investigated in the 70s too. In fact, the Born-Infeld Lagrangian is a special case of the family of no shock Lagrangians. So there's already the next in line waiting to be looked at. So this is a very systematic research project. Unfortunately, it means progress is very slow by the nonlinearity. Now think of general relativity, how many decades we are working on that. We means we as mathematicians and physicists. And so it will take a long time, but I think it's a very promising field to gain insights without speculating too wildly. And so it's really cut and dried and down to earth, I think. Long answer to a short question, sorry.
So very good. So let's see, I think there are no more questions right now. So then maybe that's a good point to stop. So let's thank Michael again for this nice talk. So thanks a lot.
And thank you all for listening and giving me the opportunity. I very much enjoyed.
Yes, we very much enjoyed it too. So and then, well, maybe I should just make an, or Claudio, did you want to say something?
No, I was just basically.
I see. Now, I just wanted to announce for the people, for the Regensburg group, I mean, we'll have our next working seminar already on Thursday morning at 8:30. Of course, this is intended mainly among us. And Magdalena will give a talk on what she's working on right now in her PhD thesis.
It will be the same link?
Exactly the same link as always, but 8:30 in the morning. And then next Friday at 2:30, I'll give a talk on this baryogenesis project where Claudio and Max are involved. Okay, good. So then thanks a lot again. And then I wish you a nice weekend and see you again soon. So
yeah.
Bye-bye.
Thanks again for having me. Bye. Have a good weekend.
You too. Thanks. Bye-bye.
Bye.